Chapter 4 is mainly going to be on probability. But it turns out that we're going to skip around in the chapter a little bit because in the book it starts immediately with probability. But it turns out that I find the flow is much better if we start by talking about a concept that we call counting first. So in your book, counting doesn't occur until 4.4. So I find the flow much better if we start with counting. And then after we talk about that, then we can go back to the beginning of the chapter and start talking about probability. So with counting, when students first hear this, they think it's just like counting on your hands and who doesn't know how to do that. But it turns out that in math, counting has a very particular definition, which is we're talking about counting things that are structured a certain way and being able to count those kinds of situations very quickly. And so this is a very important section, and it turns out that there have been entire fields of math that have come just from counting. But we're going to just talk about the fundamentals. And so to illustrate this, we're going to go through the concepts of counting with examples. We're going to learn through examples. And one example will just be a little bit more complicated than the previous examples. And by the time we get to the last example, you'll see that we'll be talking about very complicated, sophisticated types of problems. But hopefully we'll go through it gradually enough so that you won't feel it being that difficult. But I'm sure you'll let me know if it's too difficult or not. Okay, so let's start with the first example of counting. And in this example, let's say that there's your favorite restaurant, and every week when you go to it, there's a special where you can design your own meal for a special price of, let's say, $9.99, which is a bargain nowadays. And so let's say that every meal that you design has to have an appetizer, entree, and dessert. And so every meal has an appetizer, entree, and dessert. So every meal has an item from each of these categories. But let's say that from the list of entree, or from the list of appetizers from which you pick one, let's say that there are 3 options, and the entrees from which you pick one, there's 4 options, and the desserts from which you pick one, there's 2 options. And just to make this really concrete, help me come up with a list of appetizers.
Mozzarella sticks.
Okay, and mozzarella sticks. What else?
Nachos.
Nachos.
Oysters.
Oysters, fancy. Okay.
Does not fit with the other 2.
One of these doesn't belong. Okay, good. So what about the entrees? How many? So there's 4. Let's come up with 4 entrees. Yeah, steak.
Spaghetti and meatballs.
Okay. Okay, meatballs.
Yeah.
All right, what else? Hamburger.
Salad.
Salad.
Balance it out.
All right. Has to be a fancy salad to match the oysters. about another dessert?
Sunday.
Sunday. Okay, good. So now that we have these fruit items, every time you design a meal, you're gonna pick one option from each of these categories. So one time you go to this restaurant, you might get mozzarella sticks, steak, and creme brulee as your meal. Another time you go to the restaurant, you might get mozzarella sticks, steak, and sundae as your meal. And those are considered two different meals. So the question is, how many different times can you go to this restaurant and have a different meal? Okay, vote for 24. What are the rest of you guys think?
I agree.
Yeah. So another way to think about it is, if you listed all the possible meals out, and you counted all the unique ones, how many unique meals would there be? Anybody have any different answers? Okay, so let's talk about it. So it turns out to be 24, and the way that we get that is simply by multiplying all these options together. 3 times 4 times 2 turns out to be 24. And the way that we're getting 24 is, and the reason why we're just multiplying them all together, is think about if your meal consisted of only 2 categories. Let's say that your meal consisted only of an appetizer and an entree. And let's say that your meal has to have mozzarella sticks. So how many meals are possible if you have to have mozzarella sticks and there's only appetizer and entrees for your meal? Yeah, it would be mozzarella sticks with each of these 4 items in your entree. So if you had to have mozzarella sticks, then there'd be 4 possibilities. But you have these other 2 options as well. So you have these 4 possibilities for mozzarella sticks, plus the 4 for nachos, plus the 4 for oysters. So now you have a total of 12, and the way that you get that is you just multiply 3 times 4. And that's if you have a meal with only these 2 categories. You have 12. But now if you include this dessert category, now you have, imagine, the 12 possibilities along with these 2 desserts. Well, then if you had to have creme brulee as your dessert, then how many options would there be for the previous 12 plus and creme brulee? There'd be 12 options for meals, because any of those 12 combined with a creme brulee. But now if you have 2 desserts, it would be the 12 with creme brulee plus the 12 with a sundae. So then in the end, you'd have 12 plus 12, which is 24. And that would result from simply multiplying all these together. So this is what we call the rule of counting. So the rule of counting says the total number of possibilities, in this case meals, where each possibility or meal must consist of an item from each category, where the example of the categories we talked about was appetizer, entree, dessert. That total number of possibilities ends up equaling the product, or the multiplication, of the number of options across all the categories. So if we generalize it, it sounds complicated, but if you think about it in terms of the example we just talked about, then it's straightforward. Any questions so far? Okay, so let's do an example of this. Let's say that you have a closet full of clothes, and let's say that you have 10 shirts. Let's say you have 8 pairs of pants. Let's say that you have 6 pairs of shoes. And let's say that you have 2 watches. And let's say that every day when you go to get dressed, you put on one of each of these things. So the question is, how many different looks are possible? How many different outfits?
I think it's 960.
Okay, how'd you get that?
10 times 8 times 6 times 2.
Okay, very good. So just multiply all the options across all the categories together, because every time you get dressed, you have to put on one of each of these categories. So this is simply multiplying everything together. So this is 960. Any questions so far? Okay, so it turns out that in this example, every time you get dressed, you happen to put on a watch. But we know that when you go out in public, a watch is actually not required. It's only shirts, pants, and shoes that's required. So let's say, given that a watch is optional, how many different outfits are there now that are possible? So before we actually talk about the specific number, should the number be greater than or less than the previous answer of 960?
Greater than.
Yeah, so why do you say greater than?
Because you have the option of an outfit with the watch and without the watch.
Okay, excellent. So you have a certain outfit with a certain shirt, pairs of pants, and pairs of shoes. That outfit with a watch is considered a different outfit than the same outfit without the watch. So now you have a different number of possibilities. So this will be part B. If watch is optional. We know now that there's more numbers of outfits that are possible if a watch is optional. But now let's talk about how to get the actual answer. Any suggestions?
You just double it.
Okay, so a suggestion on doubling it, so doubling this number. What do the rest of you guys think?
Change the 2 to a 3, so then just multiply 10 by 6 by 3.
Okay, excellent. So one way to think about it is this watch category, now instead of having 2 options, you actually have 3 options, because if you don't wear a watch, that's actually a 3rd option. So this watch category now has 3 options associated with it. So now if you just multiply everything together, that would be the total number of outfits now, if a watch is optional. So then it would be 10 times 8 times 6 times 3 now. Any questions? Okay. Alright, so in the next example, let's say that you lose your ATM card and you're scared that somebody's gonna steal all your money. But then you remember that to do that, they actually have to have your 4-digit PIN code. So then, you're still a little bit scared because you know that professional thieves have mini computers that they can use to brute force all the possible PIN codes, where they can just plug it in the ATM machine and it goes through all the possibilities. So the question is, how many possibilities would the thief have to go through to make sure that they stumbled upon your correct ATM PIN code? So let's say that the structure of a PIN code is let's say that it has to have 4 digits, and each one is a number between 0 and 9. Okay, you're close, yeah.
10 to the fourth power.
Okay, good, so let's talk about it. So, from what we've been saying, every ATM pin possibility must consist of these 4 categories. And by the way, this is a convenient way to set it up, is that you list out all the categories as placeholders. So in this case, each ATM pin code would consist of these 4 placeholders. And then you ask yourself how many options there are for each category or each placeholder. So the first digit of the ATM pin code has how many options that are possible. So 0 through 9 is how many options?
10.
Yeah, it's actually 10. A common mistake is to say 9, but 1 through 9 is 9 options, but 0 through 9 is 10 options. So this is 10 options, and if the rest of the digits are also 0 through 9, then 10 digits for them as well. And now by the rule of counting, you would just multiply all these together. So then you would get 10 times 10 times 10 times 10, which by definition is 10 to the 4th. And that's going to be 10,000. So this is one way that we could get the answer. Another way that you could get the answer is imagining if you were to list out all the possibilities, and then imagine counting all the possibilities. So one way to do that is if you thought of a certain ATM pin code as an actual number. So for example, this string of digits, 1, 2, 3, and 4, can be thought of the number 1,234. So in that case, what is the smallest ATM pin code that you could possibly come up with?
0.
Yeah, if they're all zeros, that's the smallest ATM pin code. And then what's the largest ATM pin code? 9,999, if they're all the maximum possible number. So then, you know that there can't be any ATM pin codes that are decimal numbers. They all have to be whole numbers. So how many whole numbers are there between 0 and 9,999? 10,000. So that's the total number of possibilities. If you were to imagine counting all the possibilities from 0 to 9,999. So you get the same answer, 10,000. So this is the total number of possibilities. Any questions? All right, let's look at the next example. Let's say that at your next job, you're working for the state to make sure that there are enough license plates for everybody who's driving. So let's say that each license plate has a particular structure, where it has 6 placeholders. And let's say that the first 3 digits are the letters between A through Z, let's say capital letters. And let's say that the last 3 digits are numerals between 0 through 9. So the question is, how many unique license plates are possible, i.e. how many different drivers are possible that have this license, that have these kinds of license plates?
26 to the third times 10 to the third.
Okay, very good, let's talk about it. So every license plate has to have this configuration. So we're gonna draw out our placeholders that indicate each category, each type of thing that each license plate must have. And then you ask yourself how many options are there for each placeholder. So the first placeholder that has A through Z, how many options are there? It turns out to be 26. So there's 26 options here. And then how many options for the second placeholder? It turns out to also be 26. And then for the third placeholder, also 26. And then starting with the numerals, 0 through 9 happens to be 10. And then the same thing for the others. And so by the rule of counting, you just multiply everything together. So multiply all the options. So it turns out to be 26 cubed times 10 cubed, and if you punch this in, how do we get?
17,576,000.
Yeah, very good. So it's approximately 17 million. So if each license plate had this particular structure, then this is the number of unique drivers you could have with these license plates. Any questions? Okay. But in the previous example, we were allowed to have repetition. What that meant is, let's say that you have an F in the first position. That means you can have an F later on in the license plate as well. You can have repeats. Because we're allowing for the total full range of 26 possibilities for all of these placeholders. So that implies that we can have repetition. But let's say that now we design the rules of the license plates so that we can't have repetition. Then how many different license plates do you need to have? So this is no repetition.
Would be 26, 25, 25.
Okay, good. So let's talk about it. So then you would set it up the same way. Every license plate has these 6 categories or placeholders. And then you ask yourself, how many options are there for each one? So the first placeholder, representing the first digit license plate, has how many options? It'll have the full range of all 26.
26, 25, 24.
Very good.
Okay, there we go.
Yeah, so once you put an option there, a letter there, now you know in the next placeholder you can't repeat the same letter. So now you only have 25 options instead of the full 26. And then once you put the letters in these first 2 placeholders, now you only have how many options for the third one? 24. And then as you move to the fourth one, now you're starting with the numerals. Now you have the full range of all 10 to select one from. But once you put one there, you can't repeat, so now you have 9 options for the next numeral, and then the last one you have 8. So this is if you can't repeat, and you would just multiply all the options together. And if you punch this in, about how many possibilities are there?
9 million.
Go ahead and try to punch it in. I think it's a little bit more than that.
11 million.
Okay, should be around 11 million. Any questions? So you see, with that one simple rule change of no repetition versus repetition, we went from 17 million possibilities to cut down a lot to 11 million. So you notice that the repetition issue makes a big difference. Any questions? Let's say that you have 3 books on a bookshelf. Question is, how many different ways are there to arrange those 3 books on the shelf? So a number of ways to arrange all 3 books.
Are we assuming there's only 3 positions on the bookshelf?
3 positions, yeah. So take a moment, think about that. Okay, so 6 has an answer.
27.
Anybody else have an answer for 7? Anybody else? 9? Okay. Okay, so a lot of different answers so far, but in this example, it turns out that there's a small enough number of possibilities that it's easy enough just to list them all out and count them. So let's do that for now. So we have 3 books. Let's say that we identify the books as books A, B, and C. So this would actually be one arrangement of those three books. What's another arrangement of the same three books?
CAB.
Yeah, CAB. I'll ignore the commas. Okay, what else?
ACB.
Yeah, ACB. I'll actually do it in this order so you can kind of see a pattern. What was the last one that I erased? CAB. Okay, so what's another one?
BAC.
BAC,
CBA.
CBA,
BCA.
so you notice that there are two that start with A,
Oh,
two that start with C.
BCA.
So you need two that start with B, and it turns out to be BCA. Okay, so it turns out that there are 6. So the question is, how can you get this number 6 quickly without having to do that work?
Same thing we did with the no repetition. It's 3 positions. Since 1 is taken, then it's 2 positions, then it's 1.
Okay, excellent. So all these possibilities, you want to ask yourself, how many categories are there, or how many things are there in each of these possibilities? So it turns out that there's 3, corresponding to the 3 positions on the shelf. So list out your 3 slots, indicating your 3 placeholders, and then you ask yourself, how many options are there for each? So the first placeholder, representing the first position on the bookshelf, how many options of books are there to select from? Yeah, you have the full options of all 3 books. And once you select a book to put in that position on the bookshelf, how many options are there for the second position of the bookshelf?
2.
Yeah, then you have 2 books to select from, in which case you select 1. And then how many options for the last position on the shelf? Yeah, 1. So you, by the rule of counting, we would multiply all these together, and this ends up being 6. So this is how you get the answer quickly without having to list them all out like that. And if you look at all these positions, you kind of see why we're doing this 3 times 3 times 1, because you notice the first position here happens to have how many distinct options to select from? It has 3 of these options, so that's where this 3 is coming from. And then once you select a certain letter there, then how many options are there? If you select one particular book on that shelf, how many options are there now?
2.
There's 2. So each of these now has 2 options, and that's where this 2 is coming from. And once you fix the first book and the second book, then how many options are there for the third book? There's only 1, and that's what this 1 represents. Any questions? So here we get the answer quickly by multiplying these 3 numbers together, but notice the structure here is that we're starting with a number like 3, and we're multiplying down 1 at a time until we get to 1. So in math, this is a special operation that we call factorial. So this is what we call 3 factorial, which means that we're starting with this highest number 3, and we're multiplying down 1 at a time until we get to 1. So this 3 factorial is also indicated in shorthand with this exclamation point operation that represents a factorial. And so if you have your calculator with you, go ahead and take it out, and we'll talk about how to punch this in your calculator. So on most calculators, it's going to be enter in the number first, like the number 3, and then enter in the button that corresponds to this factorial operation. On most calculators, it will be indicated as x factorial or n factorial. But this factorial operation is usually buried in your calculator. It will be buried under some menu. It might be under like a probability menu, PROB, or it might be under a math menu. But if you have a calculator, go ahead and try to find the factorial button. I'll walk around a little bit and try to help you guys find it. let's say that we have 10 people. And we want all 10 people to stand in line. So the question is, how many different lines of 10 people are possible? So number of lines of 10 people.
I'm so sorry.
It would be 10 factorial.
Okay, very good. So you can think of it the same way that we thought about before with the 3 books, is every line of 10 people has to have 10 people in them. So those are your placeholders. So we have 10 placeholders. And then you ask yourself, the first person in line has how many options of people to select from. So you have 10 people to select from, in which you select one person to stand in that first position in line. And then once you select that person, how many options of people for the second person in line? 9 people, and so forth. So it'll be, you're subtracting 1 every time, going down, all the way down to 1. And by the rule of counting, we're just multiplying all these options together. So it's starting with the number 10, and multiplying down, all the way down to 1. So by definition, this is a factorial, so this ends up being 10 factorial. So if you punch 10 factorial in your calculator, what number do you get approximately?
3,628,000.
3 million. Yeah, so this is approximately 3 million. And you see that with only 10 people, you have about 3 million possibilities for lines. So this is an example that shows that factorial actually grows very quickly. So with only 10 people, you have a very large number of possibilities. Any questions?